Welcome back, everyone, to another deep dive in the explainer. Seriously, I am absolutely thrilled you're here. Today, we're getting into a core concept in power system protection, one that I personally like to call the balance scale that never sleeps. We are talking about differential protection, specifically the ANSI 87G and 87T standards. Imagine a continuously monitoring balance scale, right? Just carefully weighing the flow of electricity, entirely dedicated to keeping some incredibly expensive and, frankly, dangerous equipment safe. It's a brilliant piece of engineering, and we're going to break down exactly how it works. So, at its core, differential protection asks one deceptively simple question, and it asks this millions of times a second. Does the current going in match the current coming out? It's a simple yes or no, but the implications of that answer are massive. When a system is humming along normally, that answer is always yes. But when that answer is no, it means something inside that protected zone is stealing current, and that is a fault. All right, let's dive into this. Section 1, the balance scale principle. To get just a little technical for a second, we're looking at the ANSI 87G and 87T standard. This is a highly specific protection mechanism. Its entire purpose in life is to establish a strictly protected zone, typically wrapped right around a generator and a transformer, and meticulously compare the current entering that zone with the current leaving it. It acts as this absolute unblinking boundary monitor. Think back to that balance scale analogy. During normal operation, the scale is perfectly level. What goes in completely comes out. But if an internal fault occurs, boom, that scale tips dramatically. If the current entering the zone doesn't perfectly match the current exiting, it means only one thing. Something inside that highly protected zone is stealing current. A short circuit has created an unintended path, and that current is being diverted, usually with incredibly destructive force. Moving on to Section 2, TR2PDF, the primary defense. Now, let's look at the actual hardware executing this. This is the RET615 relay. This compact little unit is essentially the physical brain of the operation. Inside this device runs a specific mathematical function block known as TR2PDTF. This function is the life-saving calculator that's continuously executing the balance scale logic we just talked about. It is the primary defense for generator transformer blocks. And TR2BTDF is remarkable for a few key reasons. First, it's a three-phase, multi-slope stabilized differential stage, and we'll get into exactly what that means in just a bit. Second, it is quite simply the absolute fastest way to detect internal faults. We're talking milliseconds here. And third, it completely ignores external faults. It doesn't care about heavy short circuits happening somewhere else on the grid. It only sees faults inside its specific protected zone, which makes it incredibly selective and blazing fast. So that brings us to Section 3, the inrush illusion. Here is what most people new to protection get wrong. Let's do a quick interactive moment. Think about this for a second. Imagine a completely cold transformer is suddenly energized. When that switch is thrown, the transformer draws a massive, violent spike of current from the network. From the outside, it looks exactly like a catastrophic internal fault. So why shouldn't the relay instantly trip the breaker and shut it all down? Well, the answer is something called magnetizing inrush. This is a completely normal, temporary current surge. It happens because the transformer's magnetic core briefly saturates when it's first woken up. Get this. This inrush current can actually be several times higher than the transformer's normal full-load rated current. If our relay were just a blindly sensitive balance scale, it would misinterpret every single routine startup as a deadly fault. It would just trip immediately, causing constant, incredibly frustrating nuisance trips. Which leads us to the genius solution in Section 4, checking IDs with harmonic restraint. In plain language, the relay doesn't just look at the raw magnitude of the current. It analyzes the actual mathematical shape of the current's waveform. It turns out that massive inrush spike is highly distorted and extremely rich in a second harmonic signature. A genuine fault just doesn't look like that. Furthermore, if a transformer is overexcited, say experiencing high voltage to frequency ratios causing flux saturation, it produces a distinctly different fifth harmonic signature. The relay uses these specific signatures to essentially say, hold on and restrain or block the trip command. Think of the relay as a bouncer at a very exclusive club. A basic overcurrent relay, it just counts the sheer number of people rushing the door. But our differential relay actually checks their IDs. It checks the harmonic signature, so it can instantly tell the difference between a rowdy troublemaker trying to break things, which is a real fault, and someone who's just walking awkwardly because they're carrying a giant piece of furniture. That's our magnetizing inrush. And this brilliantly illustrates the concept of multi-slope stabilization that we mentioned earlier. Basically, the relay smartly adapts its sensitivity dynamically based on the current level. It maintains extreme sensitivity for tiny, light internal faults. But if there's a massive fault outside the zone, it actively stabilizes itself. It knows that during heavy external faults, the current transformers measuring the flow might briefly saturate and introduce small errors, so it adjusts its threshold to prevent a false trip. Pretty smart, right? Section 5. Catching the hidden faults. So the TR2PTDF function is generally on the lookout for two main culprits. On one hand, you have a bushing flashover. This is a loud, visually obvious electrical arc jumping where it shouldn't on the outside connection points. On the other hand, you have an inner turn fault, a subtle, totally hidden short circuit deep inside the winding coils. Despite being vastly different in appearance, both create that telltale differential current imbalance, and our relay catches them both. But here is a really critical question, and honestly, it's a trap a lot of newcomers fall into. Why is an interturn fault uniquely dangerous, especially considering that to an operator looking at a screen, the total load current being drawn by the transformer might look completely and totally normal? The crucial point here is understanding the physics of a shorted turn. It acts exactly like a pressure cooker. A single shorted turn might represent less than 1% of the total winding, but it creates this tiny, localized loop of incredibly low impedance. So you get an intensely high circulating current trapped entirely within that tiny loop. Standard overcurrent relays on the main lines, they're completely blind to it, but inside, intense heat is rapidly building up. If you don't catch that hidden pressure cooker instantly, the consequences are literally explosive. That intense, localized heat will vaporize the insulating oil inside the transformer. This generates highly combustible gases. Left unchecked for even a fraction of a second too long, you aren't just looking at a broken transformer, you are looking at a direct precursor to a massive tank rupture and fire. That is exactly why the blazing speed of differential protection is mandatory. Because this protection is so vital, there is a golden rule in the field. I cannot stress this enough. Never, under any circumstances, disable harmonic restraint settings just to fix a nuisance trip. When a system keeps tripping during startup, the temptation for a frustrated commissioning engineer is just to turn off the second harmonic restraint to force the machine to run. Doing that is incredibly dangerous. Disabling those filters severely undermines the security of the entire system. Real, catastrophic faults can and totally do happen at the exact same moment a transformer is being energized or overexcited. If you desensitize the relay, the transformer is flying completely blind to a real fire-starting fault happening during that startup. You must always investigate the root cause of the nuisance trip instead of just compromising the relay's logic. Okay, let's quickly wrap up the journey we just took. We've seen that the TR2PTDF function is our ultimate balance scale, constantly watching for any internal current imbalance. We've learned that it uses second and fifth harmonic restraints as its bouncers to filter out normal anomalies like inrush and overexcitation. And we've established that disabling these filters puts an entire multi-million-dollar transformer at serious risk. So, we have successfully protected our main phase lines from internal shorts, but power systems are incredibly complex, and this differential scheme actually has a tiny blind spot. What happens when a tiny amount of current leaks to ground right near the neutral line where the voltage is incredibly low? How do we catch an earth fault that the main balance scale might just miss? Well, we need an entirely different type of protection for that, and that is exactly what we will uncover in our next explainer. See you then!